here we want to talk about radiation shields. Sometimes it is our purpose to reduce the radiation exchange between two surfaces. It is the same way that sometimes you want to put insulation in the walls of, let's say, a building to avoid conduction heat transfer through the walls, so that in the winter or in the summer the temperature of the room is maintained and you don't lose as much heat to the outside in the winter, or you don't gain as much heat from the outside in the summer. The same way that we try to put the insulation in there in order for it to act like a resistance to conduction heat transfer, sometimes we want to add some resistance to radiation heat transfer. Now, in the conduction heat transfer, for example, the thickness of the thickness of that insulation matters. The thicker it is, the better it is going to insulate in stopping conduction heat transfer. In radiation heat transfer, it's not the thickness of whatever you put there, it's the radiative qualities or properties of that surface that you put there. So it's emissivity and absorptivity that's supposed to be very low on that surface that you put in between two surfaces. Let's say I have surface 1 and surface 2 like you see in the picture here. And in the middle, I want to put this surface 3 at temperature T3. And this is, we call this a single shield in a two-surface enclosure. So normally you would have surface 1 seeing surface 2 or radiating to surface 2, and then in the middle I want to put some surface that will minimize the amount of radiation, or in other words, it will have a quite large radiation resistance that will cause the total radiation from surface 1 to 2 to be minimized. Here I have a general picture of how we deal with the resistances when we put a radiation shield in between two surfaces. So on the left hand side you have radiation surface 1, and then surface 2 is on the right hand side, and then I have a shield in between, and the two sides of the shield sometimes have different emissivities. That depends on the design of the shield, but sometimes the emissivities could actually be the same. It depends really on what the type of shield is. So on the left-hand side, when you are coming up with the resistances, you would say that I have EB1, or the potential for blackbody emission, EB1 there, the same as before. So then you have your resistance for the surface 1, which is your 1 minus emissivity 1 and divided by emissivity 1A1. So this is always there as long as you have surface 1. Same way on the right-hand side, I have EB2 and the resistance for the surface 2. Again, the same way that you would have some resistance that related to the geometry of how each other and what their areas are, you do have those resistances here as well. But the difference here is when you do have a shield, what surface 1 sees is going to be surface 3. So that's why here this resistance is going to be A1F13. And then similarly, surface 2 and 3 are going to be radiating towards one another. So it's not surface 1 and 2 don't see each other because there's something in between them blocking radiation. So you're going to have 1 over A3 F32 here. And then this radiation shield, what it does is it is a surface. So it has its own surface resistances to the radiation, and it has on the one side 1 minus emissivity divided by emissivity A3, and then here it has 1 minus emissivity divided again by emissivity A3. And again, emissivity 3.1 and 3.2. These are the two sides of your shield. Ideally, you want this emissivity to be very small in order to have a very large resistance on the shield. So if I want to write the radiation exchange between surface 1 and 2, when there's one shield in between them, I'll be able to write all the resistances in the denominator. On the two sides I have EB1 and EB2, so these are the potentials. And then in the denominator I put all the resistances that are in between them. So as a result, you're going to see all these resistances here, the two on the sides for the two surfaces of your surface 1 and 2, and then this is for the view factors. And then this is all for the surface of the shield. So I can compare radiation network with no shield, which looks like this, and radiation network with shield. You can see that the resistances related to the shield are in this box, and resistances related to the view factor of surface 1 and 2 are shown here. So there are some differences, and you definitely have a couple of more resistances added. If I were to write the radiation exchange between surface 1 and 2, I'd be able to simplify this case and write it as radiation exchange for two plane surfaces with one shield in the middle, with all the areas being the same, would look like this. You can see that all the areas in the denominator that would belong to the resistances are now factorized and show up in the numerator, because all the areas are considered to be the same for the case of two plane surfaces. These are not, for example, two cylinders, one inside another. Those areas are actually not the same. But in the case of two plane surfaces, the areas are the same for surface 1, the shield, and surface 2. We also say that if you use multiple shields in between two surfaces, assuming that all your emissivities are equal, we can say that your radiation will be a percentage lower or by a factor lower than what you would have if you didn't have any shields. So based on this relation, we say that if we put n shields in between surface 1 and 2, your radiation would be divided by n plus 1 after you've actually put the shields. In other words, if you have, for example, if you calculate the radiation exchange between surface 1 and surface 2 using this relation here, the top relation, whatever we write for this network, if I calculate the radiation exchange between those two, and then I add 2 shields in between surface 1 and 2, my radiation exchange is going to be now divided by 3. So it's going to reduce by that much. If I put 10 shields, it's going to be divided by 11. Or again, it's going to be reduced by that much.